Today we're going to talk about the unit circle. Now, I'm already assuming that you're going to memorize this on your own or you already have most of the points memorized. But today we're going to dive a little bit deeper. We're going to identify a unit circle and its relationships to real numbers. We're going to evaluate trig functions using the unit circle. And then we're going to introduce domain and range of the trig functions, but we'll cover this again when we start looking at the actual graphs of the trig functions next week. All right, here's our favorite unit circle. So our unit circle is just a circle, that's all it is, on the XY axis. So we have our X axis here and our Y axis here. So each of these points on the edge of the unit circle have an X part, and that's just how far over they are on the X axis to that point, and a Y part, how far up on the Y axis do I need to go to get to that point. Each of these points are measured in both degrees and radians. So sometimes I might ask you what's the sine of 30 degrees, but I also might ask you what's the sine of pi over 6 radians, and you need to know that these are the same values. Our full unit circle, we start at 0 degrees or 0 radians. By the time I come around here, this is now 360 degrees or a 2 pi radian angle. Okay, our unit circle has an equation. All circles have an equation, even though they aren't functions, right? They do not pass the vertical line test. Our unit circle equation is x squared plus y squared equals 1. So in our circle equations, this part over here is always equal to your radius squared. Our radius squared in this case equals 1 because our radius itself equals 1. This is called the unit circle because the radius of this circle is 1 unit in length. Now this radius goes from the center to each point on the unit circle. So all of these measurements that I'm highlighting in red are 1 unit long. They're all the same length. Now, all these points on the unit circle are broken up into, they're just different divisions, different fractions of the pi, different fractions of the unit circle. So ones that I like to point out are unit circles broken up in 2 ways. It can be broken up into quarters of pi, which are going to be these blue lines that I'm drawing here. And it can also be broken up into sixths of pies or 30-degree increments, which are going to be the ones that I'm highlighting in pink. And you can see that there's some overlap with the major coordinate axes. So hopefully this makes the unit circle look a lot less scary when you realize we're just breaking it up into quarters of pi, and then we're breaking up into sixths of pies all the way around. All right, so in the past, we've probably memorized all of these XY points here, and that's great. I mean, you'll probably still want them memorized, but I'm going to teach you where these come from. So looking at our next graph, this is still the unit circle, but we have these reference triangles here. So 30 degrees and pi over 6, we can see right here, this triangle that is formed. This triangle that is formed, this angle right here is 30 degrees. This angle right here is a right angle connecting the x and y coordinates. And this up here is a 60-degree angle, just because we know our triangles have to add up to 180. Now this is a special right triangle that we've learned about before. So I'm going to redraw this triangle over here. All right, so I know that this is 30 degrees, 60 degrees, and 90 degrees. In my 30, 60, 90 triangle, I know that the smallest side is 1x, the hypotenuse is 2x, and the bottom side here is x times the square root of 3. Okay, great. Now we know that our radius, right here, is going to equal 1 always on the unit circle. So I have this equation now, 2x, this side is the ratio 2x, it's equal to 1. I can solve for x by dividing by 2 on both sides and find that x equals 1/2. Okay, so that's great. I have an x here, that's 1/2. And then I can also plug in for my x down here. This is 1/2 times root 3, which I'm just going to simplify as root 3 over 2. So as we can see, root 3 over 2 right here is our x distance, our x coordinate of that triangle. And up here, x equals 1/2, that is our y coordinate of this point. It's our y distance of this triangle. Now I could do that for this one also, which will be a 30, 60, 90, although my 30 will be up here and my 60 will be down here. So I can see why my length and my height switch places. I'm going to do one more example. I'm going to take this root 2 over 2 from my 45, 45, 90 triangle. So here we go. We have a 45, 45, 90 triangle, 45, 45, 90. We know the pattern for the 45, 45, 90 triangle is x, x, and x root 2. Okay, this x root 2 side right here is the one that coincides with the radius of our circle. So that x root 2 is equal to 1 because on the unit circle, our radius is 1 unit in length. All right, I can do some solving if I have x times root 2 equals 1. Let's solve for x. I'm going to divide both sides by root 2. I have x equals 1 over root 2. But I need to rationalize the denominator. I can't have a radical on the bottom. So I'm going to multiply by root 2 over root 2, and I'll get root 2 over root 2 times root 2 is going to get me 2. So I know over here I'm going to have root 2 over 2 and root 2 over 2 again. Okay, and again, this makes sense. My x coordinate, my x length of this triangle is root 2 over 2, and my y height is the same length as well. Now, that gets me all fine and dandy through the first quadrant, my quadrant 1 of the unit circle. I also have these points, right? This is the radius, so it's 1 unit in length. So it's 1 unit on the x-axis, and it has no height. Up here, I also have 0 units on the x-axis and 1 unit in height, because that's how long my radius is. So now let's see what happens when we want to flip over to quadrant 2. Now, I have the same exact like triangles, it's just symmetric about the y-axis, right? So I'm going to think about what I know about reflections. If I'm reflecting over the y-axis, my y values stay the same, right? These 2 points are at the same height, but my x values become negative. So that's all we're doing. We're taking, let's erase these so we can see better. We're taking these points and we're reflecting over the y-axis. Our y's stay the same and our x's become negative, and you can see that over here and over here as well. The y's stay the same, but our x values become negative. Okay, going to quadrant 3, if I'm talking about a reflection over the x-axis here from these points, well, my x values, right, this stays the same. It's the same part on the x value, so my x's stay the same, but my y's are now becoming negative. So this point here, negative 3 over root 3 over 2, that's the same x value. Our original height of 1/2, now we're just on the other side of the x-axis, so our height is negative 1/2. This pattern repeats itself. If we go over to quadrant 4, we can either think about reflecting over the y-axis from quadrant 3 or reflecting over the x-axis from quadrant 1. It is up to you, but this is how I memorize the unit circle, and it makes it much easier because I really only need to memorize this quadrant. Really, you don't need to memorize anything if you can pull out these special triangles. All right. So continuing on with visualizing our unit circle as special triangles. We're going to talk about how way back in Math 2 geometry, we probably learned SOHCAHTOA, right? We learned about triangles and how to find sine using a right triangle, cosine using a right triangle, tangent using a right triangle. So I'm going to write SOHCAHTOA on the top. S stands for sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And this is referring to the sides of the triangle in their relation to the angle that we're taking the sine, cosine, or tangent of, right? So really quickly, I'm just going to find sine, cosine, and tangent. If I'm using the angle of 30 degrees or pi over 6, those are equivalent. I would be looking at 1/2 is my opposite side, right? It's across from the 33 angle. 3 over 2 is my adjacent side. And the hypotenuse is my radius of 1. Okay. So let's say I'm going to take sine of 30 degrees or pi over 6. They are equivalent. That's going to get me the opposite, which is 1/2, over my hypotenuse, which is just 1. Anything divided by 1 is itself, so that's 1/2. Now I'm kind of going to summarize these and keep track of them at the bottom of the screen. So sine of some angle, this was our y value on the unit circle, right? If I have this point, it's going to be at root 3 halves over 1/2. So that was our y value divided by 1. On the unit circle, this hypotenuse will always be 1. So we're always going to be able to simplify this to our y value. So if we're using the unit circle, the sine of any angle is always equal to its y value. Now let's look at cosine of pi over 6. This is going to be adjacent over hypotenuse. So root 3 over 2 over my hypotenuse, which is 1. Again, this root 3 over 2 is my x value. And if I have 1 at the bottom, anything divided by 1 is just itself. And that's all, that hypotenuse is always going to be 1 in the unit circle because our radius is equal to 1. So I can summarize by this saying my cosine of theta, whatever angle that is always going to be equal to its x value on the unit circle. So that's pretty simple. Going around memorizing the unit circle, I can always find the x or y value and say, okay, sine of that angle is its y value, or cosine of that angle is its x value. Not much trickier is tangent. So if I have tangent of pi over 6, this is going to be my opposite over adjacent. So that's 1/2 over root 3 over 2. Now, probably the hardest part about this is simplifying it. But before we get there, I'm going to point out 1/2, that's my y, and root 3 over 2 is my x. So I can summarize that the tangent of theta is always going to be equal to my y value of that point over my x value of that point. Okay, but now I'm going to keep simplifying, like I said. So dividing a fraction by another fraction is the same as taking the top fraction and multiplying by the reciprocal of the other fraction. Now, 2 and 2 will cancel out, and I'm left with 1 over root 3. Again, I need to rationalize this denominator, and I will end up with root 3 over 3 as my tangent of pi over 6. Okay, so these are the 3 basic trig functions that you already know because you could do them with right triangles. We're going to talk about what's called the reciprocal functions. So if sine was y, we're going to talk about another function called the cosecant. So cosecant is going to be equal, of any angle, is going to be equal to 1 over sine of that angle, right? Reciprocal is just flipping the fraction. So if this was sine of pi over 6 over 1, now my cosecant, if I'm taking it of pi over 6, is going to be equal to 1 over sine of pi over 6. Now, I could go through the trouble of finding sine of pi over 6, and that's 1/2. And then taking the reciprocal of that, but I'm going to make it even easier. I'm going to give myself a shortcut. Oops. I'm going to say that I can just take this y value and put 1 over y. Okay, so let's summarize that below. The reciprocal of sine is cosecant. It's going to be equal to 1 over my y value. Now, following along, we're going to have secant as our reciprocal of cosine. So secant of pi over 6 would be 1 over cosine of pi over 6, which we know is going to be 1 over our x value. So let's summarize that one below too. Secant of theta is 1 over our x value. Now, tangent. The reciprocal of that is called cotangent. And I'm not even going to do that one out. I'm just going to look at this and I'm going to say, okay, it's the reciprocal of that. It's the flip-flop. It's going to be x over y. Okay. These 6 functions and their I'm calling them shortcuts below, their relationship to the unit circle, I'm going to keep that in mind and kind of memorize that and use that as I solve some examples. So let's carry these over to the next page. Copy that. Okay, so this question asks us, evaluate all 6 trig functions for negative pi over 3. Okay, so now they're throwing a negative pi over 3 at me, but I know negative just means I go this way around the unit circle with my angle. Pi over 3 is about here. I know that my point on the unit circle there is going to be, I'm going to have a positive x value because we're still on this side of the y-axis. So that's going to be 1/2. And my height is going to be 3/2 if I was mirroring positive pi over 3. But I'm reflected over the x-axis, so I know my y value will be negative there. Okay, so I'm using these x and y values to get me through those 6 trig functions. All right, let's get started. So sine of negative pi over 3 is going to be my y value. So that's just going to be negative root 3 over 2. Simple as that. Cosine of negative pi over 3 is going to be equal to my x value, which is 1/2. Okay. My tangent of negative pi over 3 is going to be equal to my y over my x value. So this is going to take some simplifying, but my y value is negative root 3 over 2, and I'm going to divide by my x value of 1/2. Okay. We already said that to deal with these mega fractions, I can take the top fraction and multiply by the reciprocal of the denominator. These 2's cancel out, and I'm left with that my tangent is negative root 3. Okay, now I can do my reciprocal functions. So I'm going to look at cosecant of negative pi over 3. So that is 1 divided by my y value. So if I do 1 divided by my y value, okay, I end up with another mega fraction. Again, we take our numerator and multiply by the reciprocal of our denominator. Okay, this is just going to simplify to 2 over negative root 3. However, I need to rationalize my denominator, and I'll end up with negative 2 root 3 over 3. Okay, so the hardest part about this is probably simplifying and rationalizing the denominator. With my secant, that's going to be 1 over my x value, so 1 over 1/2. I'm going to do the same thing to deal with this mega fraction. 1 times 2 over 1 simplifies to 2. My cotangent. Okay, my cotangent here is my x over my y value. So my x is 1/2. My y is negative root 3 over 2. Again, let's just deal with this mega fraction. 1/2 times 2 over negative root 3. My 2's cancel out here nicely. I'm left with 1 over negative root 3. However, I need to rationalize the denominator. I end up with negative root 3 over 3. Okay, this brings up a few interesting questions here. No, we'll get to those later. Okay, now you're going to practice on your own. So evaluate all 6 trig functions for 5 pi over 4. So first, figure out where 5 pi over 4 is on the unit circle. Figure out your xy coordinate, and then find all 6 trig functions using those shortcuts that we have up here. Make sure that you have these written down in your notes somewhere, these 6 shortcuts for finding the trig functions, because you will use these for a while. Okay, good luck. Please pause the video here and try it on your own. In 5 seconds, I'm going to flip to the answers so you can check your work. All right, how'd you do? Pause the screen, take a look at my work if you need to. Think about any questions that you might want to ask during office hours or Math Monday next week. Okay, here we go. Oops. Here you go. Here's another chance. Find all 6 trig functions for pi over 2. I even drew out the angle for you and gave you the coordinate. Go ahead and pause the video. Try to work these out yourselves. I will flip to the answers in 5 seconds. Okay, how'd you do? This one's a little tricky. We have some undefined values, and we're going to talk about that in a second. So looking at these 6 trig functions, we're going to kind of talk a little bit about the domain and range, periodicity, and whether these functions are even and odd. So the word periodic just means that this function repeats itself, right? So if I'm at a 0-degree angle, my point is 1, 0. If I'm at 30 degrees, my point is root 3 over 2, 1 over 2. Now, if I go around a full circle and come back, and now I'm at 2 pi because I made a full circle, plus pi over 6, my point comes back to the same point. It doesn't like double because I went once around the circle. No, we keep repeating these values over and over again for every rotation of 2 pi around the circle. So when we talk about periodicity, that's what we're talking about. How often does this pattern repeat itself? Okay, now let's talk about domain and range. So you guys are already so good at finding the range and domain of reciprocal functions or rational functions. So looking at the sine function, our sine function always correlates to our y value on the unit circle. Now, my range and domain are in terms of angle. Now, my range and domain are not in terms of x or y like we're used to. They're in terms of, or my domain at least is in terms of angle. Now, my range is in terms of x and y. So looking at my domain, there is no angle that I will not have a y value for. Every angle can be found on this circle, and at every point, there exists a y value. There's no point where the y value is undefined, right? This is a circle and it's continuous. There's no breaks in it. So my domain for this is all real numbers or all angles. I can just put negative infinity to infinity. Now, however, my range. So look at what happens with my y values. What's my lowest y value on here? My lowest y value is negative 1. My highest y value is positive 1. There's no way for me to get above a positive 1 or below a negative 1 for a y value. I don't have -2 anywhere on this graph. I don't have +2 anywhere on this graph. So my range for the sine function is -1 at the lowest and +1 at the highest. Now, these values are actually included, right? This is equal to 1 up here. So I'm going to use the big brackets. Oops. Okay. When I look at cosine, I find the same pattern that's happening. So my cosine, there's always an x value for all of these. And my range, my lowest x value is -1 and my highest x value is +1. So my domain and range are the same here. Okay. For tangent, this is where it starts to get tricky, right? All of the rest of these are fractions, and we know that we cannot have 0 in the denominator. So our domain is restricted every time we have 0 in the denominator. Okay, so let's see. Our domain, where am I going to have 0 in the denominator for tangent? I'm going to have 0 in the denominator wherever x equals 0. So let's look at our points. X equals 0 up here at pi over 2, and again here at 3 pi over 2. Okay, so my domain is going to be every angle except for the angles that are pi over 2, and that repeats every pi values. Okay, we're going to come up with another way to represent this later, but I want you to see right now, we're going to have an undefined value at pi over 2, and then again at 3 pi over 2. If I complete the circle, I'm going to have another undefined value when I come around. This is 5 pi over 2, and same thing when this is 7 pi over 2. So I'm just going to hint at our angle, cannot equal pi over 2 plus pi times k, and k is just some variable, right? Because this is pi away from that one. We go around 1 pi till we get to the next undefined value. All right, so let's clear that up and let's talk about cosecant. No, sorry, let's skip to secant, right? Because this also has x on the denominator. So we're going to run into the same domain restrictions here. We can't have an angle at pi over 2 or any multiple of pi afterwards. You can put pi times k, k times pi, it doesn't matter to me. Now, looking at the domain of cosecant up here, which is 1 over the y value instead. So now instead of looking at where the x values are 0, I need to look at where my y values are 0. So that would be here at 0 degrees or 2 pi degrees, and here at pi degrees. So my function, I'm going to have an undefined value there, right? If I have 1 over 0. So my domain can be any angle except 0 and any multiple of pi after. So I'm just going to write that as k pi, right? I can't have it at pi, can't have it at 2 pi, can't have one at 3 pi, can't have one at 4 pi. So any multiple of pi is going to give us problems for cosecant. Now, if I look at cotangent, that also has y on the bottom, so I'm going to have issues there as well at any multiple of pi. Okay, so now we're going to talk about even and oddness of the function. So think back to chapter 1. Our even and odd test was to see what happens when we plug in a negative input into f of x. If we plugged in our negative input and we got our original function, when we simplified everything, that was an even function. If we got a negative version of our original function, that means it was an odd function. So let's take a look at sine function. Okay, let's take the angle 30 degrees. If I take sine of 30 degrees my output, my f of x, should be 1/2. Now, I'm going to plug in sine of negative 30 degrees. So if I want to find negative 30 degrees, I just need to go in the opposite direction, 30 degrees. So that would be this line right here. So I'm plugging in negative 30 into my sine function. My original output was 1/2. Now I get exactly the negative output. So this is going to be an odd function. When I'm looking at the cosine of 30 degrees, I get root 3 over 2. And if we're still looking at negative 30 degrees, I'm plugging in the negative of my original input. My output, my f of x, is exactly the same. So this would be an even function for cosine. Okay, for tangent, I'm going to do the same thing. And for tangent, I'm going to look at tangent of 45 degrees because I know the tangent of 45 degrees of y over x is going to be 1 in my original tangent of 45 degrees. Now, I'm going to look at tangent of negative 45 degrees, and I'm going to see whether my tangent is negative or positive. If it's positive, if I get positive 1, like I did with my original 45 degrees, that would be the same output I was expecting. So that would be an even function. If I get a negative version, that would be an odd function. Okay, so my tangent here is going to be negative root 2 over 2 divided by root 2 over 2. All right, I can see that this simplifies to negative 1, which means that my tangent function is an odd function. Now, you can figure this out for the other three if you want on your own, or we can keep going over them. So cotangent, I'm going to pick cotangent because it's very similar. I'm just picking, putting my x over my y instead. So cotangent of our original 45 degrees, my x divided by my y, it's something divided by the exact same thing. Anything divided by itself is 1. Now, if I look at tangent of negative 45, I end up with this, sorry, cotangent of negative 45, I end up with the same situation as tangent. I have something divided by its negative self. That's going to give me negative 1, which means that this is an odd function. Okay, now let's bounce back up to cosecant. So cosecant is 1 over y. Let's do this with, let's go back to 30 degrees. If I'm looking at 30 degrees, my y is 1/2. So my original cosecant of 30 degrees is 1 over 1/2, which simplifies to 2. Okay, now I'm going to look at cosecant of negative 30 degrees. If I get a positive 2, this will be an even function. If I get a negative 2, this will be an odd function. Okay, so looking at this, I'm going to have negative 1/2. 1 over negative 1/2 simplifies to negative 2. This is an odd function. Now we're looking at secant, and let's keep it with 30 and negative 30. So my input is 30, my secant is 1 over root 3 over 2. That simplifies to, if we do all of our work all the way out again, 2 root 3 over 3. Now, my negative 30 degree angle, my secant of my negative 30 degree angle, that is still the same number for x. So these are going to come out to be exactly the same number, which means this is an even function. So you can kind of see the pattern here. Sine and its reciprocal are odd functions. Tangent and its reciprocal are also odd functions. Cosine and secant are even functions. All right, we'll talk more about this when we go over the actual graphs of the functions later in the unit.